fact, I can write it, and it's also, you can use an integral, r squared dm. For each little infinitesimal piece of mass, you say, well, where was the position of that guy? And I'm going to put a little perpendicular sign under my r's, because I like subscripts. But that means this is the perpendicular distance of that object from the axis of rotation that you're assuming when you calculate your moment of inertia. Now, a minute ago, I talked about a pivot point as opposed to an axis of rotation. The reason for that is that this is 8A, not the 7 series course, or never revision to this class. So in this class, physics is more polite in this class. So what we're going to do in this class is we're going to restrict ourselves to problems where we can always look at the object and think about the problem, where we're looking down the axis of rotation. So it's just a point in your diagram. In other words, there's some really complicated problems you may have to face in more advanced physics classes where there's a rotating object that's going like this, and there's one over here that's going like this, and this took hours of practice this morning for me to do. But you know, you have rotating objects that are going all different ways, right? And so like the axis of rotation of this guy is that way, and the axis of rotation of this guy is going that way, and then there's some torque being exerted, introduce torque tables in a minute, and the torque is in some other total direction. It can be really complicated. And in fact, some of the funnest problems, I know fun is a personal thing, but some of the funnest problems in upper division physics are like solving a top problem where you take a top that's spinning, and when you were children, you enjoy tops, maybe you still do as I do, and you spin the top, and you watch it, it will do all kinds of weird things. It'll process around like this, it'll do these little funny, right? In upper division physics, you calculate that stuff, right? And you do it using equations that are more advanced than we do in this class. And in fact, even at the lowest level, we think about what does torque mean, and what is angular momentum, and how we think about it. It turns out that there's a more sophisticated way to think about it, but it really requires a full three-dimensional treatment, and the math is pretty hairy. So what we do in this class is we're going to focus on problems where it's essentially a two-dimensional problem. Things are rotating. Like if I have this rotating chalk, I'll just assume that if it's rotating like this, then I'm going to view the problem, down the axis of rotation and see it rotating on my page. And then all I have to worry about, and also I'm going to exert torques on it. It will change its speed of angular rotation. I'm not going to try to torque it so it will change what axis of rotation it actually is going about. Anyway, so all that's to say that when you solve these problems, what we really need to worry about then is what our pivot point is and what a positive or negative direction of rotation is. We don't need to worry about the angular nature of torque, the angular nature of anyway. So we don't have to worry about that. So here's a definition for moments of inertia. Let's think about which of these objects has a bigger moment of inertia as a function about the axis of rotation that goes right through the center of the wheel, through its axis of symmetry, right? Oh yeah, right. So if the axis goes right through the center, this guy's got more mass in the middle, so he has a smaller moment of inertia, right? It's as if he had a smaller mass. He doesn't for linear, but the analogy is he's got a smaller mass. This guy's got more on the outside. So if we went through that calculation and said, let's sum up every little piece of mass in this thing, well, there's all this mass, all this brass, very heavy brass on the outside. That's a big radius. So that perpendicular radius I'm talking about is just the distance you measure on a piece of paper from the center of the object, where the pivot point is, to where the I should be careful when I say where the pivot point is. Where we're defining our pivot point, I guess I'll say it that way, because it's a little tricky to mean what I mean by pivot point. But if we say, yeah, just rotating like this, okay, let's define this pivot point. This guy is further away. This brass is further away from the axis of rotation than most of the brass was in this case, where it was really close. So that means that when you square distance, so if you have a small number, small distance, and a big distance, well, we're squaring the radius in that equation. I is the sum of r squared times m for each of those little pieces of mass everywhere, and that square makes a big difference, right? So things that are small numbers square them get even smaller, right? And big numbers get even bigger. So it makes it really matters a lot where the mass is. In fact, it matters more than where the mass, than how much mass is in those different locations in a sense, because mass is only linear with mass, right? So the contribution to the moment of inertia of a piece of mass that's like if you have a piece of mass that's twice as far away, but it's half as massive as the first piece, well, the one further away has a bigger effect because it's distance squared, even though it has less mass, right? Okay, so you can actually calculate these things, these integrals, for a bunch of different shapes, and I'm going to draw a few on board and take them through. Now, in this class, you'll never be forced, you can do it if you want, but you'll never be forced on an exam to go through some integral to calculate the moments of inertia of some extended body, right? There's a few standard, and in fact, if you've seen one of my exams now, right? See how it works? I tell you everything, right? And you walk in there with a sheet with all this formula, you've got it all, right? You can write down the moments of inertia of all your favorite objects on your sheet, and in fact, they'll be on the exam if you need them. But I think it's worth knowing how to do this, or just thinking it through for a couple examples, just so you get some intuition for how this works. You'll get answers, you'll recognize your answers wrong, you'll understand it better. So let's think about this, perhaps the simplest case. Suppose you've got a bar, you've got some beam, and it's very thin. It's so thin we can neglect its thickness. All we have to worry about is where the mass is along the length of the beam. Let's say it's got length L. So it's got length L, all right? And it's got some mass per unit length. Often I write that as lambda. Lambda starts with an L, sounds like a length. So we often use lambda for a density, but not a density in terms of volume. It's a density in length, so it's mass per unit length. So to be the total mass of the bar over how long it is, that's what lambda must be, right? So if it's a 1 kilogram bar and it's got a length of 1 meter, it's got a density of 1 kilogram per meter, right? Okay, great. Now we have to choose, well, if I want to calculate its moments of inertia, I have to decide what pivot point to choose. By that I mean I have to decide where my origin is for this integral I'm going to do of r squared dm. Where's r equals 0 going to be in this picture? Well, let's do it two different ways. Let's calculate two different moments of inertia. Let's do one from the center and do one from the edge. So first of all, where's the center of mass going to be in this object? Lambda is a constant. So we've got this bar. Where's the center of mass going to be? This is a stupid question. Where's the center of mass going to be? Right in the center. You bet. Didn't have to be that way if I chose the mass to be not unevenly distributed. But if it's evenly distributed, you know it's going to be right in the middle. And you can do the calculation with the integral, but you're not going to bother. You know it's going to be right in the middle. So let's try this as our PP, which is a little sort of PG-13, but I mean just pivot point. At least for my daughter, I would use that. Pivot point right in the center, right? All right. So given that, let's go ahead and do the calculation. And I'll even do this. I'll put CM as a subscript in my moments of inertia to remind me that the one I'm talking about in this case is the moment of inertia about the center of mass. Now this wouldn't fully specify it for most objects, like for this wheel, right? After all, I could have an axis that goes through this way through the wheel, and then it goes rotating like that. That would give me a different moment of inertia than if I had the wheel rotating like this. Now you have to drive your car pretty hard to get your wheel to go like that, right? Or have a pretty bad situation going on, end over end. But it's a rigid object. It would rotate this way if I spun it in the air like this. I could do that, right? And if I want to use Newton's second law for rotation, go through all this stuff and calculate, I have to worry about the fact that that's a different moment of inertia than this one. So for some objects like this, it matters. This isn't enough to tell you which one you mean. So just make sure you know which one we're talking about. I mean, it'll always be a case pretty much in this class that the moment of inertia is going to go that way. Like that's the one you care about because wheels rolling on the ground. In this problem, it doesn't matter though. If you go to the center, oh no, it does matter, doesn't it? I take it back. You could go through. So there's a whole plane of angles. Like I could rotate the bar this way, right? And I could rotate it this way, but I could also rotate it this way. So in fact, what I'm saying is not true. I was going to say, oh, it doesn't matter. There's only one object for which I sub CM is all you need to know, or one class of objects, and those are objects that have what kind of symmetry? Spherical symmetry. If you have a distribution of mass that's spherically symmetric, then that means it doesn't matter what direction the axis goes through. It goes to the center of mass, it's the same moment of inertia. But this object doesn't have spherical symmetry. It has a lot of symmetry though. It's got cylindrical symmetry. That means that there's a whole plane. Anyway, all right, enough of that. So great. So what is that going to look like? Well, it's going to be an integral from, let's see, my origin is right there. So I'm going to go from minus L over 2 to positive L over 2, right? And every little location, what is my infinitesimal mass? Well, it's going to be my mass per unit length times the infinitesimal distance of that little piece of mass. So what I'm doing is I'm integrating the contribution from every little, what is that? That's lambda dr, right? Some little tiny dm, right? And this thing is what I mean by r. That's my distance from the origin, right? And I'm going to multiply this by r squared. So this thing is what I mean by dm. So that's just what I mean. This is a perpendicular distance because I'm talking about an axis of rotation that comes just out of the board, say, or it could also be this way, vertically. But it's not coming in at some crazy angle like that. I'm talking about an axis of rotation that's perpendicular to the bar itself. Yeah. Lambda is the same as one I have right up here. So all I mean by lambda is the mass per unit length. So if you have a 2 kilogram bar, and its length is 4 meters, it'd be a half a kilogram per meter. Multiply that by dr, you get an infinitesimal amount of mass. This thing has units of length, this has units of mass per length, kilograms per meter. You multiply these together, you get an infinitesimal mass. That's what I need, infinitesimal mass. Great. What do I get? Well, integral of r squared, I can do that one. Start at the third over 3. Does everyone agree? And now I get the limits of integration. L over 2, and minus L over 2. All right. Let's see, I plug in all of it. It's 1/3 times L over 2 to the third power minus L over 2 to the third power. So many bookkeeping issues here, but I'm keeping my head straight. To the third power gives me a minus sign. One where there's actually 4 minus signs right here. Does everyone see that? So what's 4 minus signs? It's equal to positive 1. Great. So these are being added to the same thing. I can just put a 2 in the front. See how clever I am? So I get L to the third over 2 to the third is 8. Does everyone agree with that? And now I got 2 over 8. That's 1 over 4. 2 times 4 is 12. So when the dust clears, I get, oh, I made some mistake, didn't I? Oh, I left out lambda. So I need lambda. I had the wrong unit, so I got a mistake. So lambda right here. So I need lambda right here. Now I get 1 over 12 times lambda L to the third. What is lambda times L? Lambda times L is just mass. So if I express it in mass, I wind up with 1/12 ml squared. Does everyone see that? I like writing it that way because I can just read off the units really easily. Oh, that's kilograms, meters squared, and L was given in my problem description. So and maybe the problem said, okay, you got a certain mass a certain way. There it is. So great. So what I find out is that I get something that's got units of mass times length squared, and it's got a 1 over 12 in front. Now suppose we did the same integral, we calculated the moment of inertia, but now we do it about a different point in the object. Let's take a point on the end of the object. So again, an object that's got distance L, but now here's our pivot point on the far left side of this object. So it's rotating like this, right? Coming around. Or I can do it, well, actually I can do it this way. Let's say that it's in the board. So that means that it's rotating like this, right? So it's a nice big circle on the board. So if I do that, will this have a bigger or smaller moment of inertia? Will this be a bigger or smaller moment of inertia than up here where it's rotating like this? Is more mass further or closer to the pivot point in this case? Some of you are saying it, but does everyone see what I'm asking? Same object, but if I rotate about the center of mass, in fact, the center of mass is a special point, and that is the point about which, if I rotate about that point, right, mass is as close as it can be to the pivot point. In this situation, the mass is further away on average from the pivot point, and we saw that it goes like r squared, this moment of inertia. So we're going to get an answer that better be bigger than the one we got before for the new moment of inertia. Does everyone see that? Maybe I'll even write ICM, just to remind you what this is. Okay, there's my box answer, ICM equals that. So now let's do this moment of inertia. Well, the same integral, but now we go from 0 to L. Oh, it's actually 0 to L, right? Of what? Of lambda dr times r squared. Well, we're going to get exactly the same, I'm going to cut to the chase, because it's the same integral, so I get the same functional form, but now I plug in different limits of integration. I plug in L and 0, right? So what do I get? I get the 1/3 in the front like I got before. I get the lambda, but now I get L to the third power minus 0 to the third power, so I think that's my answer. Does everyone see that? So maybe I'll put end to indicate this isn't the center of mass moment of inertia, it's the moment of inertia about the end of the object, right? And I get this. And so this is in fact 4 times bigger than this is. Does everyone see that? Oh, and this again, I missed my m. Oh, no, I didn't, because I didn't write it in yet. 1/3 ml squared. That's why I just substitute once again lambda for m times L. M over L, excuse me. So good. So that's equal to 4 times, right, the other moment of inertia. So that's really important. You get different moments of inertia depending on where you measure them, and it makes sense. So if you think about a circus performer, right, which I'm sure you often do when I'm up here, you have some guy, or man, woman, going on a tightrope, and what do? They have this giant beam, really long beam they hold, right? And when I was really young, I go to the circus and I see this, and the longer this beam, wow, it's really impressive. Turns out it's easier with a longer beam to walk on a tightrope. That's why they do it. And people aren't stupid. Now they're walking around up there, and you're going to fall, it's painful. So they've got this long bar. The longer the bar is, for the same mass, just make it thinner and longer. The longer the bar is, then the bigger your moments of inertia by L squared. And what matters is the center mass one, right? Because that's where you're holding it. You don't hold it on the end, then you just fall over. You have this big, right? So you hold this bar, and the longer it is, the bigger moment of inertia, the bigger your angular momentum, how do I say it, the greater your inertia is, the harder it is for a torque on you to throw you off the bar, to throw you off the tightrope. So that's actually, and where's the situation come from? Well, it's this is exactly the calculation they did before they decided what bar to use, right? Although I shouldn't say exactly, there's one more thing I have to do, just to relate this to torque, so we're getting there. So when we get to torque, we'll bring it up again. One thing to mention here is that there's another way I could have calculated this. So what I did was I calculated different moments of inertia for the same object, and one of them was about the center of mass. It turns out that for any object, there's a nice relationship between the moments of inertia about the center of mass and the moments of inertia about any other axis through the object that is parallel to the initial axis you had. And that's called, cleverly enough, it's called the parallel axis theorem. Okay, the parallel axis theorem says that the moment of inertia, any moment of inertia about some axis in some problem, right, is equal to the moment of inertia of the center of mass for the same object plus an extra correction term. And this is just the total mass of the object times the distance d away between the distance between those two axes. I get the units right, unless it's squared. So let's look and see if this is held here. I think it is, right? Because what is the distance from one axis to the other in this problem? It's L over 2. Does everyone see that? The axis of the center of mass was right to the center of the bar. The second axis we just chose to do that was at the end. Well, that's L over 2 away from the center of mass, right? So the two axes are parallel. They're both into the board. They're separated by a distance d of L over 2. So in this problem, it'd be L times L squared over 2 squared is 4. So that means that it's a quarter ml squared. And let's see, is that true? Well, so does a third plus a quarter equal to 12? That's the question. Let me check real quick. Sure, will do that in my head, but here, I'll do this. So the statement is, all right, is that true? A third, yeah, because all the other factors are the same, just ml squared everywhere. So the question is just whether a third plus a quarter. What does that equal? Well, let's see. I have to take a difference here. Oh, I see what I did wrong. I want to add, if I want to make this, if I want to check this equation, I center of mass is a 12th, and this thing is going to be a quarter. So the question is whether a 12 plus a quarter equals a third. That's the question, right? So let's add these up. Let's see. So if I get 12, fractions are off. 1/12 plus, what is this? 3/12. Sure enough, it's 4/12, and that's 1/3. Good. So the parallel axis theorem would work for us. Well, of course it would, but it's just that there's two different ways we can do the calculation. And there's times when it's way, way, way easier to use parallel axis theorem. For example, suppose you know this, what the moment of inertia is about this, an axis going through the center of this wheel. But in some problem, you want to use this as your pivot point over here. Suppose you want to do that. Well, parallel axis theorem is easy, right? You just take the distance, which is equal to r. It would just be mr squared. Just add mr squared to the moment of inertia about this axis when it goes to the center, and that tells you the moment of inertia is over here. Now to do the integral, can you imagine the integral? You can nasty. Do the integral of all the mass inside this object, because all these distances, you have to measure them, and you can't use polar coordinates in a convenient way because you aren't going from the center of the circle, you're going from the edge of the circle. It would be a terrible calculation, but you don't need to do that. Parallel axis theorem saves the day, right? So it's a useful formula, and it gives us a good intuition because it quantifies the thing I said a minute ago in sort of just common sense, which is the common sense statement I made, that the moment of inertia about a random object or some axis that goes through some random part of an object, it's always going to be bigger than the moment of inertia through the center of mass, right? For a parallel axis goes to the center of mass. That's the smallest you can make moment of inertia, and that equation tells you because m times d squared, no matter, that's always a positive number. You always get more moments of inertia to go away from the center mass axis. Yes. Oh, sure. What is md squared in this problem? Md squared equals, well, m is m, d is L over 2. That's the distance between those two different axes. The one goes to the center of mass, and one goes to the end of the object. If we square that, what happens? Well, both the L get squared and the 2 get squared, so you wind up with a quarter times ml squared. And that's how it is that I knew that to check that the parallel axis theorem is true, I needed to add the 1/12 ml squared plus 1/4 ml squared. I better arrive at 1/3 ml squared, and it worked. Yeah. As soon as I do stuff in class, it takes so much chalk as it is, and I feel like I've bludgeoned you guys with algebra. But sometimes I'll leave off a step or whatever, and I'll get questions after. I was like, well, you just write out the last step. So let me know if I leave stuff out and you can't figure out what the heck I wrote. Yeah, let me know. Okay, great. So that's parallel axis theorem. That's a specific, very simple example. The simplest example we could actually work with that involves an integral. The very simplest example is a wheel that's actually got all its mass right at the surface of the wheel, because then all the mass is exactly r away from the center, from the axis that goes through the center of the wheel. So what's the moment of inertia? Suppose I have a wheel like this one, with brass around the outside, but I hollow it out. Suppose I burned all the way out of the middle. That would never do. But suppose I removed all the center of this thing, so that I just had the hoop. We have a hoop over here, actually. Yeah, hoop over there. So in that case, if we remember the moment of inertia about the axis that goes through the center of mass, right, that goes straight through the middle of the object, that's just the radius r squared times the mass of the object. You're done, right? No integral, no sum, right? Because you say, well, wait, there is an integral. There's mass distributed in all these different locations. Yeah, but they're always the same distance away. It's always r away. The perpendicular distance from the axis is r. So you know it's just going to be the total mass times r squared. Simplest case you can hope for, right? So if you have, so that's why I'm describing this. If you have a hoop, right? You get the idea. And it's hollow. Then about this, if this is your axis of rotation, you'd say, oh yeah, that's just going to be what did I say? M r squared, where this is r. That's your radius, right? And then if you have a solid wheel, suppose you have a solid wheel. So it's solid. Right, this is a hollow wheel, a solid wheel. Solid wheel, moment of inertia is going to be bigger or smaller than this one for the same radius. It's got the same radius, right? We'll just have a smaller or a bigger moment of inertia than this guy. Same mass. This guy's got mass down, he's got mass down. Who thinks this has a smaller moment of inertia? Only a couple tokens. One person with 2 hands up. Who thinks this is going to, thank you for that vote. Who thinks this is going to be greater moment of inertia? Oh, well, people are not voting. But, I mean, a couple, like equal numbers of like some tepid, So let's think it through. It's the same mass, same radius, but does this one have more mass toward the middle or more mass toward the outside? Outside. More mass toward the outside. Is that bigger moment of inertia or smaller moment of inertia? Bigger. So which of these has the smaller moment of inertia? The solid sphere or the hollow sphere? Cylinder. Solid will have a smaller moment of inertia. And in fact, it's 1/2 as big. You do the integral, you get a half in front, if I'm not mistaken. You just look up my cheat sheet. Sure enough, I got it right. Yes. I'm sorry, say it one more time. I'd say the opposite. So bigger moments of inertia is like having a bigger mass for linear acceleration. If you have a bigger moment of inertia, that means for the same torque, for the same set of forces acting on you in the same locations, which we'll go through in a minute, if you have a bigger moment of inertia, you will react less. You will speed up less. Your angular acceleration will be less. So when I roll these two wheels down the hill, they experience the same force of gravity acting on their center of mass. They experience, well, let's see, is it the same force of friction? Anyway, they experience force of friction acting in the same places in the same direction. But who got to the bottom first? The one with the mass on the outside, or the one with the mass on the inside? The one with the mass on the inside got to the bottom first. He went faster. And another way to say that is if I go over here to this demo, and I've got this object over here, we saw how fast he accelerated when I took this off of here. So he starts to, you can see that mass over there going down. He's accelerating at that speed, or that amount of angular acceleration. If I replace this solid disk with one of equal mass, but distribution, so the mass is more on the outside, it's on the outside. So now this has a bigger moment of inertia, and I suspect that it should have less of it, and they have the same mass, I was told. I didn't weigh them. I guess I weighed them. Then it should have a bigger or smaller acceleration, angular acceleration. Smaller.